In the previous video, we have seen most of the things about rate of a reaction, but under one condition where it was independent of temperature. That is, we assume the temperature to be constant throughout the reaction. But now, what if the variable temperature is also involved? That is, the temperature is not constant. So, about that we will be concentrating in this video. So now the very basic equation which relates the rate constant with temperature is famously called as the Arrhenius equation. The Arrhenius equation is nothing but K is equal to A e power minus Ea by RT. Now this K is nothing but the rate constant of a reaction. This A is nothing but called as the pre-exponential factor, or it is also called as the Arrhenius factor. It is also called as the frequency factor. Now in this exponential term, there are three terminologies which is involved. The first one is known as the activation energy, which is denoted by Ea. Ea is nothing but the activation energy. And R we already know, R is nothing but the universal gas constant, and T is nothing but temperature. So now in this Arrhenius equation, K is equal to A e power minus Ea by RT. We already know what K is. K is nothing but the rate constant, and T is nothing but the temperature, and R is nothing but the universal gas constant. But then A and Ea are the new terms for us in this equation. A is nothing but just a constant, like we have already defined it to be a pre-exponential factor or the frequency factor. Now E is specifically called as the activation energy. Now before understanding what activation energy is, we have to have basic clarity on the other terminologies so that we come back to this term and discuss what activation energy is. Now, so the first term which we are going to discuss about is the threshold energy. Now the threshold energy is nothing but the minimum amount of energy, which the reactant must possess, to convert to products. So now this is nothing but the energy which, or you can also understand in this way, the energy that must be, the energy that the reactant must be having for it to convert to the products. Now let us come back to the activation energy, and we can learn how to relate this threshold energy with activation energy. Now the activation energy is nothing but the energy which is required by the reactant so that the total energy becomes equal to the threshold energy value. So now, according to this definition, activation energy is something like the energy that must be needed to be added. So now we can compare this definition and the previous definition. Now this is denoted denoted by EA. Now we can write an equation ET is equal to EA plus ER. Now you may be wondering what this new equation is. This is nothing but based on the previous two definitions. Now this ET is nothing but I use it to represent the threshold energy, and you may be wondering what this ER is. This ER is nothing but the energy which the reactant possesses already before the starting of the reaction. Now this is the energy of reactant. Now you can understand EA very well. Now the energy that must be added to the reactant so that the total energy becomes equal to the threshold energy is called the activation energy, which is EA. Now let us apply the concept which we have just learned in terms of a graph. So we can draw a graph between the energy of the reaction and the reaction coordinates. Now the graph will look somewhat like this. So the starting point is nothing but the term which we use to represent it like ER. ER is nothing but the energy of the reactants. Energy of reactants. And the topmost point is nothing but the threshold energy, which we represented it by ET. Now the bottommost point is nothing but EP, which is nothing but the energy of the products. Now essentially this is not the ending point of this graph, but at this point the graph starts to become a constant graph. So some arbitrary point we decipher it to be the energy of the product. So that's why we are taking this point as the energy of the product. Now, how do we represent activation energy in this? Now we have already related the threshold energy with the energy of the reactants. ET is nothing but EA plus ER. Now threshold energy is nothing but the difference between threshold energy and the reactant energy. So the topmost point of the graph was the threshold energy, and this was the starting point was the energy of the reactants. So now this is nothing but the threshold energy EA. That is the difference between these 2 points. This is nothing but EA. Yes. So from this graph, also we can actually come to a conclusion that lower the activation energy, this is the most important point, faster is the reaction. Because the activation energy is that energy which needs to be added to the energy of the reactants so that the reaction has or possesses some energy which is equivalent to the threshold energy, and then smoothly the products are formed. So if the energy gap, which is nothing but the threshold, which is nothing but the activation energy, is greater, then obviously you will have to supply more energy for the reaction to proceed to completion. So that is why lower the activation energy, faster is the complete reaction. So now that we know the Arrhenius equation, let us derive the Van Hoff's equation from the Arrhenius equation. So say at temperature T1, the rate constant of the reaction is K1, and at temperature T2, the rate constant of the particular reaction changes to K2. So now for this first condition, if we write the Arrhenius equation, we get K1 is equal to A e power minus EA by RT1. Now, for the second condition, similarly, we write this Arrhenius equation. We get K2 is equal to A e power minus EA by RT2. So now here one important point to be noticed is the value capital A doesn't change because it is the frequency factor. It is constant, and the value EA also doesn't change. There are few dependencies for EA too, but in this case only temperature changes, so that is why EA doesn't change. Yes. So now let us name this equation 1 and the second equation 2. So now taking log on both sides for both the equations, we get log of K1 is equal to, it is obviously the natural logarithm. So the base E, so log A plus, so by using the log properties, I directly bring it here. So we get minus EA by RT, because log of e power minus EA by RT is nothing but minus EA by RT. So similarly, for the equation number 2, we get log of K2 is equal to log of A minus EA by RT2. This is T1. Now, here we have one similar term in both the equation, log A and log A. So let us subtract these both equations which we have got just now. So by subtracting we get log of K1 minus log of K2 is equal to log A and log A will get cancelled, and we finally get EA by RT2 minus EA by RT1. Now we can use the another logarithm rule. We can write log A minus log B as log A by B. So following that rule, we can further simplify this equation to be log of K1 by K2 is equal to, now this EA by R we can take it out because it is a constant. It's equal to EA by R into 1 by T2 minus 1 by T1. So this is nothing but the Van 't Hoff's equation which we have just derived from the both the equations. Now final equation we can write it as the Van 't Hoff's equation, which is log of K1 by K2 is equal to EA by R 1 by T2 minus 1 by T1. And if you want to introduce logarithm to the base 10, we have to just multiply a constant 2.303 into log of K1 by K2 is equal to A by R 1 by T2 minus 1 by T2. So this is nothing but the Van 't Hoff's equation. So now let us understand the role of a catalyst in a chemical reaction. So we already know the definition of the catalyst. It is a chemical substance which alters the rate of the reaction without itself undergoing any permanent change. So this is the definition of a catalyst. It can either speed up a reaction or it can slow down a reaction. There are additional two terms called promoters and catalytic poison too, but the definition of these substances are different. But then here we concentrate only on catalyst. Now here with respect to this chapter, chemical kinetics, catalyst basically, this is the most important point, catalyst decreases the activation energy. That is, the activation energy was the energy difference or the energy which must be provided to the reactants in addition so that it reaches the threshold value and then the products of the reaction are formed. So this catalyst, by decreasing the activation energy, thereby eases the reaction to proceed to completion. So let us understand it with the help of a graph. Now this represents the energy of a reaction as usual, and this is the reaction coordinates. It is assumed. Now the reaction, now suppose the original reaction without the catalyst happens like this according to this curve. Now if we add a catalyst, what happens is this will become the case. That is, the dotted lines now represent the reaction with the catalyst. So basically, in the first reaction where it was without the catalyst, this whole barrier was the activation energy initially. Now the second reaction, the energy gap has significantly been reduced, as we can already see diagrammatically. Now this is the new EA. So basically, the purpose of the catalyst is to reduce the threshold energy. That is, the threshold energy of the first reaction was, the threshold energy was far high than the second reaction where the catalyst was there. So it basically reduces the threshold energy so that the energy that needs to be supplied to the reaction reduces. So it thereby decreases the activation energy. Now let us understand it mathematically. So let us say, so the catalyst basically changes the rate of a reaction. So let us say before adding the catalyst the reaction rate was Ki, and after adding the catalyst the reaction rate is Kf. Now according to Arrhenius equation we can write Ki is equal to A e power minus EA. Let us say the activation energy initially was EA1, and after adding the catalyst the activation energy got reduced to EA2. Now since this is the first equation relates the initial rate, so this is nothing but minus EA1 by RT, and one more equation we can write relating Kf and EA2. Similarly, Kf is equal to A e power minus EA2 by RT. Now we are considering same temperature here because we are just adding the catalyst and we are assuming there are no temperature changes during the addition of the catalyst. Now let us divide both the equations. We get Ki by Kf is equal to e power EA2 minus EA1 by RT. So Ki by Kf is nothing but e power the change in the activation energy EA whole divided by RT. Change in activation energy A is nothing but the final activation energy minus initial activation energy. So this is the final equation. This corresponds to the addition of the catalyst in a chemical reaction. Now let us come to the collision theory. So now this theory basically states that the reactant, this theory assumes the reactant molecules to be hard spheres Now it assumes the hard spheres to react with each other when they collide with each other. So these spheres collide with each other to produce the products. Now this relation which collision theory proposes is somewhat similar to the Arrhenius equation. Here is why. The equation is nothing but rate is equal to ZAB into e power minus EA divided by RT. Now in this equation, now this resembles somewhat to the Arrhenius equation because this ZAB is nothing but a combination of A and another fraction F, which is nothing but the fraction of the effective collisions. So now what is this effective collisions? Now the collisions, not all the collisions lead to the formation of the final product because sufficient energy, that is the kinetic energy, has to be there between the reactant molecules which are colliding so that the products are formed. That is, you can also understand with respect to the threshold energy. Now once they collide with a specific speed or specific kinetic energy, then only it will cross the energy barrier of the threshold energy and then it will lead to the formation of the products. So not all the collisions make an effective collision. An effective collision is that collision which positively contributes to the completion of the reaction, that is the formation of the products. So that is known as the effective collisions. So how can we define ZAB now? So why is it AB? We just denote it as AB just because we take it uh, we take the reference from this reaction. A plus B gives C plus D, where A and B are reactants. That is why here we represent it as ZAB. So this ZAB is nothing but the collision frequency of the reactants. This is the actual collision frequency of the reactants. That was an ideal case where we took it to be A, assuming that all the collisions are effective collisions, but here not all the collisions are effective. Here it is nothing but the total value A into the fraction of the effective collisions, that is nothing but the fraction of effective collisions is nothing but effective collisions by total collisions. Total collision is nothing but the sum of effective and ineffective collisions. Now we have understood what ZAB is. AB is A and B are reactants, so that is why we represent it as ZAB. Now, is this the final equation for the collision theory, which is the rate is equal to ZAB into e power minus EA by RT? The answer is no. It is because one more factor is involved here, which is nothing but the steric factor. The steric factor is nothing but we generally used to uh, use that term in organic chemistry where we learn about stereochemistry. We discuss about the spatial arrangement of the atoms or molecules in space. So here we introduce one more term called P, which is nothing but the probability or steric factor. Probability or steric factor. Now here the collision theory also states that despite having All the conditions to undergo the effective collision, the two reactant molecules must be in a specific orientation such that they react with each other. So, including the steric factor also in the final equation, along with the fraction of effective collisions, we get the final equation of the collision theory to be rate is equal to P times ZAB into e power minus EA by RT. This is the final equation of collision theory where P is the steric factor, ZAB is the effective collision frequency, and EA is the activation energy, R is the gas constant, and T is the temperature.